All right, so now we're going to get into step 4.5, testing our model. So one thing that I want to emphasize that was a small mistake on my part was that in the previous piece of coding, this line was indented one place further, but we want to bring that outside of the loop. So that's a small correction. Otherwise, everything else should be good. And now we're going to go into how to compare our code versus something more official like Scikit-learn, right? That people use and canonically is the go-to. So what we're going to do first is we are going to load our model. Then we're going to, from Scikit-learn linear model or linear regression. Okay. So before we use that, we're going to create some fake data. And this fake data is going to be as simple of an example as possible, especially in interviews. It can be a little bit tough to, one, make a more complex data set, and two, understand the complex data set. So what we want to do is make it as simple and understandable as possible so we can compare our two models. So first, what we're going to do is we're going to define our X values. These are going to be 10 records, essentially, that have one feature each. And this feature will be a single number. Now, because both Scikit-learn and our model expect a 2D matrix or list of lists, we're going to just wrap these around and make them their own list each. All right, next, what we're going to do is define our M and our B values. So a slope of 3 and an intercept of -2. So these are the parameters we want our model to learn. We're going to create fake data based on these values, and then hopefully, if we did everything right, Scikit-learn and our model will be very close. Now, our Y values, which we're going to synthetically generate based off of these previous 3 parameters, are going to be mx, okay, m times x, plus b, or each x in the bigger X array. So this is list comprehension, just saying for every single row or every single one of these, multiply our slope by that value and add our intercept, y equals mx plus b, and that should be y. So now what I'm going to do is just put in some print values so we can see exactly what this data looks like. X, y, and or x, m, and b we just defined. Now y is going to be exactly the 1D list of numbers, just like our model and Scikit-learn expects. So now what we're going to do is we're going to train and predict with sklearn. Scikit-learn linear regression equals linear regression. Now we're going to do Scikit-learn linear regression dot fit x and y. We're then going to say y hat 1 equals sklearn linear regression dot predict on x. Okay. And lastly, we're going to print an f string for substitution and say sklearn prediction is y hat 1. Okay. So what are we doing here? All we're doing is a very simple train and predict on our X data. Now, usually, obviously in practice or especially in production, you would do train test splits, hyperparameter tuning, XYZ. Today, well, none of that matters. All we're doing is just testing to see how similar our model is to Scikit-learn. So none of that is really very relevant. So now that we have that piece of code going, we're going to do the same thing. We'll say train and predict with our model. Say our model, right? So my linear regression equals my linear regression. We're going to set our iterations to 1,000. We're going to set learning rate equals 0.1 because we don't want that to be too high. Otherwise, the learning will diverge and the parameters will go crazy. So we're going to give it 1,000 iterations point 1, we're going to do essentially the very same thing here. So we're going to say my linear regression, my hat 2, my linear regression. Okay, let's just check over that. Looks good. And we're going to, one more thing. I'm going to print a line here that says my linear regression intercept. So we're going to see the parameters that it learns with the intercept and the weight vector. So this intercept should be as close to -2 as possible. And the weight vector should just be 1 weight, and that should be as close to 3 as possible. So let's run this. So here, what we're going to do is actually set our learning rate to 0.01, because 0.1 still diverges and becomes too big over 1,000 iterations. So let's set that learning rate to 0.01, and let's set those iterations to 1,000 still. And now, running this code, we see that Scikit-learn predicts exactly what we fed in as the y vector. So it's spot on, and ours is going to be very, very close, though not exact. Here we see 1 is very close to 1.03, then 4.025, 7.01, 10.01. So you can see that these values are very, very close. And the parameters that it learned, the intercept was very close to -2, and the weight vector, or the single weight value, is 2.99, or very close to 3, just like our target. So that's pretty much as close as we're going to get without a bunch of small optimizations and things like that that Scikit-learn has that are very fancy. So for the point of the interview, here we have proven that our model is 1, generalizable because we have coded it in such a way. 2, we've passed in a very simple data set that we have defined and understood the parameters that we're using and that we're looking for the model to learn. And now we've shown that that's exactly what happens. It's very close to Scikit-learn's prediction, which is a really good benchmark. And if you have time in interviews, this is always very helpful to do. Not all interviews are going to require you to actually compare solutions, as long as the interviewer feels you have a very good understanding of what's going on and that a small typo here or there, they're not going to be on you too much. That's not what the point of the interview is. It's to make sure that you have all this code in place, your pseudocode is very, very solid, and that you're able to essentially construct all the different components of the model. All right. So now what might happen in the interview is, let's say you solve this and you have some time, which this should take you maybe probably 20, 25 minutes. They'll probably ask some initial questions, ask you to test your understanding. That'll take 10 to 15 minutes, 20 to 25 minutes here. You might have 10 to 20 minutes left. In that time, you might be asked some follow-up questions to test your understanding. So let's go through a couple likely follow-up questions. 1, how to generalize to more than one feature. We already did that. Now, this is a common follow-up question because a lot of the time it's very easy to quickly get some pseudocode down and the y equals mx plus b version that we saw. So most people will create a linear regression like that, but if you want to just go ahead and honestly do it right the first time is the best way to put it, then here you go. How to update the model with more data. So let's call that a warm start, right? Let's say I've already trained on some data, but I want to keep updating because I've got new data. So that can be done by simply having the train flag, where you can say self.train, and you can also have a define update function. An update function, rather than calling initialized parameters and saying, okay, we're going to do it at 0, in this case, you don't need to initialize anything. You just take the current self-intercept, you take the current weight vector, and again, you just start throwing it through our, our training loop. So you do this again, you'll get some new numbers here, and you can just say self.update count, or number of times update is called. And you can have that self.update plus equals 1. So gradient descent versus one-shot. When would you use one over the other? Always, when you're being asked in an interview, I don't say always, but 99.9% of the time, they're looking for, do you understand how to code up a gradient descent? Now, linear regression is relatively unique in the sense that it can be computed with a one-shot algorithm. So one-shot algorithm is literally just doing matrix math on the input data vector and the answer, the y vector, and you can just get the weight vector as a consequence of literally just a quick equation where you throw the no need for gradient descent, no need for updating parameters iteratively, all that. Gradient descent is usually better for massive data sets, can be done online learning where you're being fed data over time. You can also generally tweak it more easily in terms of different gradient computations and stuff like that. So in general, it's a little bit more complex, but it's a lot more rewarding and flexible. So space and time complexity. What is the space and time complexity of linear regression? So the time complexity is going to be the number of rows times the number of columns times the number of iterations that you do. Okay, so that should be relatively straightforward. Space complexity. So space complexity is just O of the number of rows. So the only thing that we're keeping here as a parameter that scales linearly is the weight vector. So the weight vector is going to be the same, or sorry, the number of columns. It's going to be the same as the number of columns. Other than that, yeah, there's not much. I mean, in the predict function, you're going to need to keep a variable that's the number of rows. But again, you can just kind of explain your way through both of these. There's no like, oh, it's O of this, and that's like the final answer. It's like if you're predicting, it's number of rows. Otherwise, it's number of columns to store that in self.weight vector. And otherwise, if you're ever confused on the inner workings of a model, I usually like to go to Scikit-learn. You can always just read the Wikipedia page. That's kind of tough sometimes because they tend to over-explain really hard. But Scikit-learn has tons of examples you can always go through, look at how it's implemented, and actually look into the code if you need. You can look at the source code itself. And again, production grade Python source code used in a gigantic library used by millions of people is going to be a little bit obscure and have optimizations and stuff like that. But if you have any questions, that is a pretty decent place to start. Good luck, practice, and you're going to do just fine. Thank you, everyone.